Good. Thank you for joining our webinar this morning. I'm Mike Searle, your host today, and with me is Josh Bigger, who will be presenting with us today. We begin. I'd like to go through a couple of housekeeping items. First of all, we'll be using the chat and the QA functions, the WebEx program to be able to capture any questions. We will probably be holding most questions until the end when we can review and answer the questions. So please be patient. Don't be disappointed if we don't get immediately to any questions you might send. Please do send them. Our presenter today is Josh Bigger. Josh is a pressure metrologist with Fluke Calibration, located in Phoenix, Arizona. Josh has been in pressure metrology for 15 years. He joined for around 15 years. He joined Instruments in 2004, and after coming from the Air Force, he holds a from Business Electronic Systems from Wayland Baptist University and MBA with highest distinction from Embry-Riddle Aeronautical University. And of course, Josh is a pressure metrologist with Fluke Calibration. Josh, can you take it from here?
Thanks. Good evening, everyone. Today is going to be understanding pressure controller / calibrator specifications. And sorry, technical difficulties with the audio. All right, let me restart. I got my set back on and Bluetooth working. So, all right, thank you, Mike. Good morning, everyone. About pressure controller and calibrator specifications. We, as a manufacturer of Fluke Calibration, use these specifications to describe a pressure controller. Today, we'll cover what is a pressure controller calibrator, the types of specifications, a pressure controller delivers and measures pressure, and the goal is to look at the different types of specifications and how to interpret their significance for your application. Pressure controller calibrator. A pressure controller is an instrument that provides automated pressure control and measurement of hydrostatic pressure. They perform two functions. They control pressure and they measure pressure. And the fluid is in a stable condition, as I mentioned, hydrostatic. Even though the pressure controller is like sometimes pulse pressure, using temperature to control pressure, a essentially static situation to best of its ability. Now, there are controllers that are made to work specifically for gas or oil, which is pneumatic or hydraulic. And pressure controller that is pneumatic only. One that's hydraulic is hydraulic only. You couldn't interchange them because the way the plant and contend with between oil and gas. Examples of some pressure controllers that Fluke manufactures on the bottom, starting at the far left bottom, that is the 7050 series controller, which is a formerly Ruska Instruments, which uses the quartz boron tube sensing technology. This controller, you can have it configured with any range from about 5 kPa to or 10 inches of water up to about, I think, 20 psi, which is with the QBT, or 1,000 psi with a quartz reference pressure transducer. The controller on the right is a hydraulic only, and it's a PBCH, formerly DH Instruments pressure controller, which uses a reference pressure transducer or a utility silicon-based sensor. The mag you can get on this controller is about 30,000 psi, hydraulic only. And model to our family of pressure controllers is the one in the middle, which is the 6270A, which is a tubular pressure controller. It can 5 ranges, I think 42 ranges you could interchange, and from ranges from negative 100 kPa for negative gauge, all the way up to 20 MPa or 3,000 psi. Things can take on multiple different forms, and they can be combined with each other. So it's important to realize the type of specification and how it's applied to your instrument. Pressure controllers is typically in percentages. And percent of reading specification, percent of scale specification, percent of span, percent of range, and commonly parts per million. That way you can just deleting zeros if you have a lot of zeros before your number, just to make it a little bit easier. Now, a few minutes to go through what each of these mean and the differences between them. All right, with precision, the specification is proportional to the pressure. That is, pressure increases, so does specification or error. As pressure decreases, the specification also decreases with it. And as you can see in the top right blue plot I have, you see at from 0 to 100% of full scale, or kPa, however you want to interpret this graph. As I go up in pressure, specification is linear proportional to that. The propagation that I've noticed is at 0 or lower pressures, like at pressure, if it's a gauge sensor, you have no specification because it's 0 times 0, which is 0. So that leads to the next 2+ manufacturers, even Fluke, have a minimum threshold where 7% of reading device or instrument, there's a minimum threshold at which the repeatability and other contributors where the specification cuts off and becomes like a floor or a threshold specification. The reality of the percent of reading down to 0 would be have specifications at 0 for this, and with feedback in the industry, old which takes care of that problem. So that threshold, the red plot, it's reading 0.1% of reading to 50% of the full scale ice. And then anything below 50% is a floor specification of 0.005. Now, at lower threshold, like as the green plot on the right, it's good. The 0.0% of reading down to 25% would do a floor of 0.005. So knowing the threshold and cutoff could determine on how well the pressure controller is designed and how well the information is relayed to you from the manufacturer. Percent scale, Here we saw that the percent of reading specification is proportional to the pressure applied, no matter what the full scale of the sensor range is. Now with the scale specification, the specification is proportional only to the full scale or the range of the instrument. No matter which pressure you're at, it's a constant throughout the whole range. For example, in this plot, range is a 100 kPa full scale gauge sensor. Of 0.01% of full scale would yield the 0.01 kPa expression at all pressures throughout the range. Full scale versus span and range. Some manufacturers interchange these terms. They use the same term for all types of sensors. I'm going to try to break it down into the three cases which I normally see in the industry. Now, full is normally abbreviated as F, typically the maximum pressure of the range. The scale most positive value, if it's a positive sensor, or if it's a negative gauge only sensor, it could be the most negative value, but it's usually the maximum number. Typically maximum minus minimum. Where span is also designated as full span with the abbreviation of FF, just like full scale. So it's important to know if it's really full scale or full span, because that could double your specification if you're not careful. Normally used when device has multiple ranges installed, or you can downrange a sensor with software or coefficients. So it is important to know if range is of the maximum range or like a downrangeable range of the sensor. Here in this plot is the scale and full span. If I had a percent of device, 0.01% scale would yield the blue line, which is 0.01 kPa. But if it was based on the span of this device, negative to 100 kPa, the span is actually 200 kPa, which would yield 0.01% times the span of 200 kPa, which would be 0.02 kPa. So it was double the specification if you weren't sure on if it was full scale or full span. There's a range that Fluke used for the RPT device. I'm sure if other manufacturers use this term, they may use the same meaning for it, but all ranging typically take advantage of allowing the instrument or sensor to create a lower full-scale downrange, either equal to or lower than down to a threshold. This allows you to use their reading same specification at the default range or down to a lower range to have better rangeability. The reading for this type of technology is, because when we were characterizing transducers, we noticed that if you don't take a sensor to its full scale, you could improve hysteresis and essentially improve your patient. So if a calibration at full scale meets the specification, you only downrange it to 30% and do the same 30%, you have improved specifications. So you can have that turned down 0.01% down to a lower full scale. The plus full scale specification is fairly common in pressure devices. This specification includes a proportional error and an offset added together. It's in a reading with the threshold. As you can see in this plot, percent of reading with the threshold is the blue plot, where you have the percent of reading down to percent threshold. You have a percent of reading plus a lower specification equal to the red plot added together. Knowing the difference between plus or make a huge difference in specification. PPM is used a lot, especially with higher accuracy and precise sensors, because you have a lot more zeros in front of the significant number. Part per million, 1 ppm is 0.001%. Example, part per million, we say ppm, which is 10 ppm scale, which is the same as 0.001% of full scale. And likewise, a 5 ppm of reading would be 0.025% of the reading. I think the big way of this presentation is to be aware of percentages and how they're used. I mean, we use like a language when we talk about pressure controllers. When doing specification instrument, we it's percentages first, and then we typically take those into a pressure value. We do percentages is because it will simplify and provide a single specification for a model or family of instruments. Like I mentioned, it is always recommended to convert like units to or pressure units when comparing instruments. On the left, we have some examples of that. So 100 psi full scale with a specification of 0.05% of full scale. Our reference standard, but it has a 5 times better specification of 0.0% of full scale. So are we this? Is it going to be good enough to calibrate? Is it 5 to 1? It's really 1 because even though the percentages are when a full-scale device, if you multiply value into pressure units, it's really a 1-to-1 test accuracy ratio. So in this case is extremely important. Overall, when describing the instrument, there are a number of things we do to describe it. First aspect is, what is the capability of the instrument? This brings to the most important is the pressure media. Like earlier in pressure calibration, it's pneumatic or hydraulic, and that specifies the instrument type, what it can be used to do. The term pneumatic, we use typically nitrogen or air, and a clean, dry source. Hydraulic, typically oil or water. The oil is a mineral oil, non-corrosive oils. Keep clean. I mean, there are other types of oils that are used in the industry with different densities, but typically for calibration, we try to use the cleanest oils possible for the process. In most cases, hydraulic or pneumatic is going to be used for lower pressure applications, and hydraulic is used for higher pressures. Between the two usually depends on the engine and resources available to you. Calibrate some 10,000 psi sensors with oil. It's safer and less volatile than if you're using gas. But then there are also considerations of cleanliness and contamination. So always based on the application and with safety in mind. The thing to consider is the pressure range. What's the pressure that the instrument can control and measure? That's on the highest pressure which the instrument measures. Then, if you need a negative sensor, this will be very important to you. You don't want it to stop at 0. If you have a negative sub or gauge sub ATM pressures or negative gauge pressures, span, which is a calibration branded term. You can have it with multiple RPTs available in an instrument. And a use set span that is less than or equal to the QRPT span, and that is the rangeability of the QRPT. Terms used to describe control performance of a pressure controller: control stability and precision. You have to see how quickly you can get to the point. That's something like response or time to set point. Overshoot describes how far the pressure may go over the set point before stabilizing at the set point. The volume is important in the pressure controller is controlling into. That could increase your time and stability numbers change. And lowest controllable pressure and ultimate pressure. We'll talk about these specifically. So pressure is naturally unstable. Pressure will change based on temperature effects and leaks. Variations in temperature will cause changes in pressure, just as leak system will cause changes in pressure. It is a leak-free system, but it's not always possible to be 100% leak-free. I mean, no matter how well it's sealed, it's just a matter of a leak you can deal with in your process. Pressure calibrations, we need a method of stabilizing the pressure. We need some maintain pressure around a set point with a hold limit. Just the idea that pressure will change due to temperature changes, and just placing pressure into a volume changes the temperature, and it takes time to stabilize. So the controller has to be able to compensate based on the excursion into the set point and for fluctuations in volume changes and temperature changes. You can different control algorithms as two plots. The plot shows a pressure excursion, a slower or a lower C control around hold limit. Now the bottom is a more rapid control, where it's to hold the pressure to the same limit, but the frequency at which it increases and decreases pressure in the hold limit is more frequent. So Fluke calibration has multiple pressure controllers. We don't always use the same terminology for them globally, mainly because different sensing technologies and product families with a historical significance. T-series pressure controller, we have controllability specification and the ready tolerance. Now the controllability specification is the limit around the set point that will control within, with that is based on the intrinsic design of the instrument and the way the firmware controls pressure. Ready is a user-specified value that you can set, and that pretty much determines when it's ready. If you're remotely communicating with the device, that's the ready flag. That all right, pressure is ready. Or the LON or the display will come on the front screen to say, hey, the pressure is ready. And that are ready, that ready light will go away. PP4 series with QRPTs limit and the control vision. Hold name as a limit around the set point that the pressure controller will control within, and that is user settable and default setting of 0.01%. Is the minimum possible setting for hold limit. pressure controller, the 6270A, you potential for many different ranges installed, and it is proportional to the supply pressure to the instrument. The precision is 0.001% of range with a 2-to-1 turn down. So if I have 3,000 psi installed with the supply pressure of the 3,300 psi, that gives it 0.001% of the range down to 10%, or a 10-to-1. So any pressure range below 300 psi, which is the 1 threshold, assumes that same floor of control precision. Lower pressure range, 300 psi, for example, and you have a subpressure of 330 psi, you can 10-to-1 turn down at the 30, which is 10 times better. The specification that should be considered is the lowest control pressure. The range is the lowest controllable pressure absolute mode, not main gauge mode, because in gauge applications, the lowest pressure is typically vented, which is 0. And actually 0, you can actually zero it at the condition. But in loop mode, 0 absolute, there would be no molecule system, and that is not feasible with using the resistance inside controllers. It would take a really long time to pull to a 0, and vacuum pump you would need would be probably overkill for the application. On the lowest absolute pressure a controller can achieve, and the vacuum pump, the tubing diameter, the length of the tubing, leaks, and devices that are hooked up to the controller will impact that. Now, how the controller will control is impacted by many factors. The size of the volume is controlling into, the pressure change, the fitment of the test port, the pressure you're allowed to overshoot at this point, how close to be to that point when you're ready, what stable pressure, and low absolute pressures determine or impact how fast a pressure controller will control. So an examination for control speed has some factors around it. 78 example that's to the specification. So the time to that point will be 10 seconds, which is typical. A 10% step in pressure change, that a 50 cubic centimeter volume to a of 0.005% range. And could change to a larger value or even smaller value depending on the excursion step. Like if you go 0 to 100%, it could take maybe more than 10 seconds. It's the volume to 500 cubic centimeters that could also increase the time to set point. Rate of flow, the rate of flow restrictions will also this. So an instrument control pressure and some specifications related to pressure control. Now discuss how an instrument measures pressure. Typically, in specification of a sensor, vision, which is comprised of linearity, hysteresis, repeatability, temperature, the measured uncertainty, and the delivered pressure uncertainty. So again, we have linearity, hysteresis, and non-repeatability. So non-repeatability is separated from linear hysteresis but just generalized, they're together here for the precision specification. The linearity is the deviations of the linear output of the pressure sensor, which I had a straight line going through the plot left. You can pretty linear down to about 20%, and then kind of take off to down to, so that'd be a leak, that could be a linearity issue with the sensor, or just part of the sensing technology. Pretty much the residuals that you see based on a straight line from the minimum to maximum of the calibrator range is the error from an influence that is dependent on the mechanical memory of the sensor. So we're going to just plot it here. The pressure curve is on the bottom, and you can, when I hit full scale at 100, if I start coming back down in pressure, the descent riding above the ascending curve. The hysteresis of the sensor, and as I mentioned here, you may be able to minimize this depending on or having a downrange, where if you only went to 50% of the sensor full scale, this could be half or even smaller. So hysteresis, linearity make up your conformance specification of a sensor. Ability is the ability of the sensor to repeat a pressure pretty much at conditions in a short time frame. Long stability, or sometimes just referred to as stability, is mainly the slope drift of a sensor, or if it's stability or slope stability. But this long term is strictly its slope stability. So things in sensors could change over time. That is why we calibrate, to ensure that we're within our state specifications. Long-term specifies the maximum amount of the sensor is estimated to drift over a period of time. Normally, this is a percent of reading over a period of time, and a period of time provides guidance on the calibration interval that we assign to it and the cost. If you don't sensor that's stable, that could directly impact your cost of purchasing the controller, and also the cost of pure calibration. If you have to keep a sensor within a tighter tolerance, you may have to calibrate every 3 months as opposed to a year, which increases cost. So it's all based on the aviation and the sensing technology. So most materials that react to changes in pressure also react to changes in temperature. For example, if you have a well-characterized controller, you pretty much may have a thermometer where its pressure controller works as a thermometer than a pressure controller, because its rate of temperature changes. Different handle this is to characterize the sensor over multiple temperatures and compensate, or to keep the sensor at a constant temperature, or a combination of both. Like the QBT in the 7250 series is kept at 50 degrees C, but is also compensated. That just minimize temperature effects. So using a pressure controller calibrator, it is important to use the controller within the operational temperature range that it was characterized in. They have to buy a pressure controller and characterize it yourself. The sensor are already characterized and assign some limits on the temperature range. And then if you're outside of that temperature range, we provide a specification that you should expect to see outside of that range. So overall, uncertainty, it combined effects of all components that could affect the measurement. For a pressure controller, there's precision, stability, reference used, and temperature effects. Are within the control of the manufacturer of a pressure controller, but industry expects the manufacturer of pressure controllers and sensors to provide our bit of measurement uncertainty for the patient. And we put notes what range, and if you're using outside that range, it is typically up to the customer to quantify that. And back on use controllers on site that aren't in a controlled laboratory, and we can provide information on what you would expect to see if you're not within the stated range of the pressure controller. So we do our best to provide all the information possible that goes into the measurement uncertainty of the instrument, which includes components that we include in the uncertainty, how they're related to each other, the disk type and confidence interval of each component. And that's the beginning. Then once the user buys the equipment, they should create their own budget, considering things like the information we provided, the calibrator needed, whatever reference they're going to be using to calibrate it, environment it will be used in. So measured is delivered. So on the P4, the measured uncertainty includes all components associated with the measurement function, not control function. Delivered uncertainty includes everything above, plus the stability of controlled pressure. This is when the pressure is assumed to be at the set point and not read directly. Before measurement uncertainty comes in multiple classes of uncertainty for the QRP. There's F class, S class, and P class. F stands for full scale class, which is a 0.015% of the Autorange span. This for S class is 0.01% of reading down to a 30% fold, and the premium or P class is 0.008% of reading. The F class is for F class, full scale class. The auto span is at least 30% of the QRPT's range. And for you can have up to 2 QRPTs installed for more stability. Some PSI high range, 100 PSI low range, that'd be a 10-to-1, where you can use the same percent of audience span down. You get each sensor down to its minimum 30% and get the same performance. Standard class for PPC4 is a 0.0 reading percent to 100% of the QRPT span. And that low 30%, it's going to be 0.01% of the 30% value. And once again, this product can also have 2 QRPTs installed. Same concept, just a improved accuracy or specification, 0.008 as opposed to 0.01%. But Autorange this percent and really 9 per QRPT span, because it's 30% of 30%. And you can see that when you Autorange down to 30%, the red plot, you bring that reading specification down to 9% of the total span of the QRPT. A has multiple module sensors available, and this is the M200 pressure measurement module class, which is only a 0.02% a full-scale sensor. Ranges in this class and this can also be used in the 2270A, 2270A. Standards can only be used, or this 2271A calibrator can only use the PM200 modules. It has electrical measurement capability, heart communication for cal transmitters. 70A can use P600, which are the point center reading devices, or the PM200 0.02% of full-scale devices. It can be used in the range of negative 100 kPa to 20 MPa. Now there are PM600 ranges available, which were in the QRPT product line. It's modular module that makes it easier to have more rangeability instead of buying multiple instruments. Earlier, PPC4, you can only have 2 pressure ranges per instrument. Now you have a 6270A chassis where you can buy up to 5 modules, and you can have like pretty much 3 instruments in one. It's very important to understand the specifications of the pressure controller to make sure it will meet your application. And basically, knowing between percent of reading, percent of full scale, percent of span, and how the manufacturer interprets specifications for your application. And pressure controls 2 things: controls pressure and measures pressure. So there's specifications that are directly related to control, and there's specifications that are directly related to measurement capability, and a combination of those 2 specifications. So how the common control specifications, measurement specifications will fit application will help you decide on what best suits your application. Thank you for joining today. Here are links for some seminars and some pre-recorded seminars that we have provided. And feel free to message me questions, or if you would like this presentation, it'll be sent out. Thank you very much. Good day.
Thanks, Josh. We're open to questions now. If you have any questions, please do send them to both the host and presenter, either via the Q&A feature or the chat feature in X. We do have a couple of questions. First, can water be used as the medium in a controller?
Yes. On what type of controller it is, an inherent hydraulic pressure controller, yes, you can water. Today I see a mixture of water, alcohol. That way you have less of mold forming or contamination. The alcohol will like prevent from growing. But yes, if you order a pressure controller, 7600 PPCH series, I have seen those with water, distilled water. But you will order a 7250 or a 6270 with water. Only.
Thank you, Josh. A question came to send a link of the presentation. There will be an email that is followed up within the week with the presentation and some additional information. So there will be additional information coming. Another question that came in is, what is the best controller to calibrate low pressures from 1 to 30 inches of water?
So we have specific ranges in the 270A target that drift range. We all have a PPC4 with the bottom gauge 15 kPa sensor that has a dual volume unit that is volume for stability. It's a insulated volume. You wouldn't want to use a higher range device that will for ranges. We have specific ranges targeted for that range. So 6270A, the B2.5 VA sensor, and the 4, the BG15 kPa sensor.
Please do send any questions you have. I think I'm here. I'm trying. Okay. Yes, there's another more specific question, and I believe it's similar to a previous question. It says on 7615, which one of our hydraulic controllers capable up to 40,000 psi. Can use other fluids other than the HT230 slide.
Well, if your instrument is manufactured with a certain fluid, its control algorithm could be tailored for the density of that fluid. And if you were to change it out at your site, you would pretty much purge out all this fluid is manufactured with and where similar density fluids will work that way, but it is very important if you have to change out fluid due to cleanliness issues that you purge it properly. But typically, the control made for a specific fluid, its control, its product is made for that fluid.
Okay, another question came in regarding if a controller is available for vacuum range.
As in negative gauge pressure, or vacuum as in like a sensor measuring absolute pressure? We don't have 6270 has multiple ranges that have negative gauge that can handle vacuum. We don't have a vacuum module sensor that you just plug in, but some absolute sensors available, low absolute A100K full scale, that will do atmospheric pressures in absolute mode. But vacuum sensor, like if you're expecting the controller to like be used as like a thermal or Pirani sensor, not the application, which is just used at a single point zeroing sensor. It's mainly used as a sensor with a calibrated range.
Pressure controllers are often used for low absolute pressure type sensors in the typically 1 psi or more, though, depending on the performance of the sensor. Other question did come in specifically about the negative differential pressure, and this specifically applies to the 0 to 40 inches of water negative differential pressure range. And what about controlling at those ranges?
So 40 inches of water, that's about 10 kilopascal, and yet we do have that well, metal like line is the numbers make it easy to know the range of the sensors available. Like we had let me go back to a previous slide. Depending on the accuracy needed, or the limit uncertainty, see that our model line, if you're doing gauge and positive gauge, the BG in front of the range number, that means bidirectional gauge. So as sensors here, like this the third one down, the PM200 BG40K, that means it can do bidirectional full span of 40 kPa, so negative 40 to 40 kPa. That helps to model knowing what the range that you could do. Doing inches of water, to that would be the 35K, which is about times the full scale. But if we switch to the P100 ranges, we have 15K, which is negative 60 to 60 inches of water, which is closer to your negative 40 to 40 inches of water. So that'd probably be a better sensor for you. It has a better uncertainty. But yeah, all numbers help distinct. It's bidirectional gauge, which is the G, gauge, which is a G, or absolute, which is an A in model of the range.
And I would like to add also that for the absolute best performance for those low draft ranges, we offer a special version of the 7250 controller, 7250 line controller. Uses the quartz boron tube for very good performance at the very low pressures, and that's for the ultimate performance at the draft pressure. It also has extremely good control down there. Typically for controlling low differential, including negative pressures, in addition to a low pressure supply, there'll also be a vacuum pump attachment, so that attached to the supply to the controller, so that the controller can tune in between that vacuum value, the negative gauge value, and the pressure. A verifying question came up on the 7615 and using a different fluid. It asks if we use HT200 on the 7615, does it have to be calibrated for that fluid?
We don't, there's like 25 fluids that I've seen in our fluid pools, but our references we use which is monoplex DOS. It's a mineral oil. In our references, we can't just put any fluid in our piston gauge, so we usually have an interface between the 15 and our piston gauge. It could be a level interface, or it could just be a pressure tube where fluids meet at the same head height. So it doesn't matter what fluid that you have in your instrument, as long as you have an interface between your reference system and you for the head correction difference between those.
So I think Josh explained earlier that typically will purge an instrument or flush the fluid out of it, assuming that the fluids are compatible. Typically, performance will not be highly dependent on, or measurement performance will not be highly dependent on which type of fluid other than that head correction. So typically, other than the complication of calibrating in different fluid versus operating fluid, which is usually taken care of by the calibration house, or if it's being sent to calibration for service, there shouldn't be a big effect on the performance. Just make sure that head correction is appropriately accounted for. Um, I don't see any other questions. We'll leave the line open for just a couple more minutes in case there are additional questions. Please send them via chat or QA features and send them to both the host and the presenter. Question did come in, and the question is the pressure pump included with the controller?
Well, 2615, yes. Everything needed to control pressure, no matter if it's pneumatic or hydraulic, it's inherently instrument. Except like for the gas devices, you need supply pressure or vacuum externally. We have other products that have self-contained vacuum pressure sources. We have a 22 pressure controller that has an internal vacuum pump and a pressure pump up to 300 psi. But for the 7250 series, you have to supply pressure or a vacuum pump for it to control pressure. 7015, you have to apply drive pressure to really drive the pump. But the drive pressure to build up the hydraulic pressure, it's self-sufficient after that.
I don't see any other questions. Thank you for joining us today. We will be sending out, following up with an email with information, including the presentation itself. Please feel free to email either Josh or myself with any questions. Joshua.bigger, BIGGAR, @fluke.com, or Mike.Searle, SEARLE, @fluke.com. Thank you.
All right, thank you, everybody. As Mike, please email with any questions, and have a good day.